Well, good day, everyone. Thank you very much for joining our webinar. This is Peter Clark from xSeriCon in Hong Kong. And today I'm going to talk for a while about CHAZOP, or Control System HAZOP study. I'm going to assume that you're reasonably familiar with HAZOP already, and base most of my comments on the similarities and differences between the way that we conduct regular HAZOP and control system HAZOP. The technique known as CHAZOP, which is usually considered to be abbreviation for control system hazard and operability study, though some people think of the C as standing for computer, so then it becomes computer HAZOP. The background to this is, if you think about how we will normally do process hazard analysis on one of our processes, we tend to look in quite a lot of detail at the potential upsets with the process equipment itself, which is what you can see in the green box on this slide. And we will do a pretty rigorous HAZOP study looking at failures, misoperations, malfunctions, unexpected behaviors of process equipment. We will also potentially look at issues relating to, for example, power loss or utility failures, as you can see in the blue boxes, and that might be more appropriately studied by different techniques such as fault tree analysis or reliability block diagrams. But what about the part in the middle in the red box that connects them together? We tend not to look at that in so much detail. I think partly because we tend to assume, without really thinking about it, that it's fail-safe. And I'm going to show you a few examples later of why that may not be a reasonable assumption. So I think one of the reasons why it's important to focus on risks that arise from upsets in the control system itself is that in contrast to process system upsets or process equipment upsets, a single failure in the control system could lead to multiple consequences. If you imagine that we have one part of the control system, maybe the CPU or an I/O card malfunctions, it could knock out a whole lot of control loops, of alarms, maybe even some safety barriers that are built into the system. And we need to be able to take into consideration the fact that we might lose a lot of functionality all at the same time as a result of a single point of failure. And the second point is, as briefly mentioned already, we should not assume that the control system is really fail-safe. For one thing, safe can mean different things to different people. For one person, safe means coming to a shutdown condition. Somebody else may think that safe means put into a safe kind of holding condition. A third very important issue that we really need to be aware of these days is cybersecurity. The control system is potentially vulnerable to malicious attack, either from within the organization or from outside. And there's an ever-increasing number of recorded cases now where quite significant upsets have occurred to control systems as a result of some kind of malware attack. Probably the most famous incident is from a few years ago now, an incident called Stuxnet. If you've never heard of Stuxnet, then I highly recommend that you do a bit of searching online and find an article to read about it. I feel that everyone involved in process safety and process management should know about Stuxnet and how to make sure that it doesn't happen in your organization. A fourth issue that is peculiar to the control system is that we have application software in there, which is dedicated to our own process. And we need to think to some extent about the reliability of that software. How can we assure its reliability? And we'll talk about that a little bit more later. And a final consideration with regard to studying the control system upsets is that when we do that study, it generates useful system availability data and it helps us to understand the logical architecture of our control system, which is important input if we're trying to do a RAM study in order to predict the availability of our plant as a whole. And in case you're not familiar, RAM stands for reliability, availability, maintainability. So when do we think that it would be worth doing some kind of risk analysis or upset analysis on the control system? Well, my suggestion is that if we have a history of problems or a history of spurious trips or system downtime that may be caused by issues in the control system itself, that's an indicator that we need to do a more in-depth study. A second indicator would be if we are implementing a new control system or system that's new to us, which is more complex than we're used to, or maybe one that's of novel design or different from what has been used on our facility before. A third indicator would be if the control system is interconnected with other systems, for example, through network connections. And a fourth, because that introduces potential outside sources of vulnerability and also means that an upset in our control system may also have an impact on other systems as well. And the fourth indicator would be if we believe that the potential consequence of a failure in the control system could be quite significant in terms of the amount of harm that could ultimately result to the process as a whole. And I will explain in a few minutes about how we can evaluate the severity of the consequence. Now, one of the difficulties with discussing CHAZOP is that when you look in the literature, what little literature there is about CHAZOP, you find quite a number of different kinds of study have been labeled with the name CHAZOP. So there is a fair bit of confusion about what CHAZOP actually is. And in particular, there are 4 types of study that you may sometimes see referred to as CHAZOP. And these are the 4 that you can see on the screen now. However, for this talk today, I'm going to focus on the second one, the one marked with an orange box, which is the one that I would personally consider to be CHAZOP, and the others I would give different kinds of name to. But let me run through them briefly just to try to clarify what these types of studies actually are and what we can use them for. So the first one, FMEA, Failure Modes and Effects Analysis. Now this is a calculation that we can do at our desktop. It doesn't require a workshop study, and its purpose is to take a very well-defined, clearly defined system, such as a control system, or a specific piece of equipment, such as a turbine or a compressor, and to calculate its predicted failure rate in various different failure modes. And we can identify the different ways in which it can fail and calculate a failure rate for each of those. And the FMEA can also give us very useful data, for example, relating to the effectiveness of different testing methods that we can do. And will also tell us things about what kinds of critical spares we may need to want to keep in stock. So that's FMEA. CHAZOP, Control System HAZOP, which is the focus of our talk today, is a workshop study that focuses on the control system specifically. It systematically goes through a series of prompts or questions relating to the study in order to find points of weakness or vulnerability within the system and determine what would be the failure if those either failure events or other kinds of upset event occur. So that the purpose of that then is to try to identify where are the weaknesses and maybe whether some redesign should be implemented or whether some additional safeguards are required or maybe some additional training or information provided to the operators. The third type of study that sometimes is called CHAZOP, but which I think that's potentially confusing, is software analysis. Now, this could be software criticality analysis, for example. And this study is sometimes referred to as software HAZOP. But really, it's nothing like a HAZOP study, so that's quite a misleading name, I think. That would be an assessment to determine, first of all, how robust is the application software for a specific process application in terms of how well has it been designed and developed, and to try to assess the consequences of software failures in order really to decide how much effort do we need to go into in order to confirm that the software is as accurate, as correct as we can get it. And then the fourth kind of study, human factors analysis. And if you know anything about human factors analysis or ergonomics analysis, you know that it can be a very wide-ranging study, of a whole set of different studies, really. What I'm talking about specifically here for today is how looking at the ways in which the operator interacts with the control system and to determine what is the potential within that interaction for misoperations to take place, that in a way that the operator could perhaps unintentionally cause an upset in the control system, which could then lead to wider consequences. And that also has sometimes been referred to or included in CHAZOP, but personally I would exclude that because I think that that is a different type of study that uses a different methodology. So next thing to think about is supposing we're doing a set of studies, usually centered around the regular process HAZOP study, which you can see in the center of this diagram. How would CHAZOP relate to that? And when is it appropriate to do CHAZOP study in terms of the sequence of studies that we need to do? Now, I know this diagram looks a little bit busy and complicated, but we can mainly just focus on the HAZOP and CHAZOP boxes. So for this talk today, I'm going to distinguish between two different studies, which might both be called CHAZOP. On the left side, you can see a box that says batch mode CHAZOP. Now, what I'm referring to there is, supposing you have a computer-controlled sequence of operations, for example, a batch operation. Or it could be something like a startup or shutdown sequence for a piece of equipment. One of the questions we need to ask is, what kind of faults can occur or upsets can occur in the control system that controls that sequence? The reason we want to identify which types of fault are credible and which are really not credible is so that we know which types of upset to consider in the HAZOP study. As if we go into the HAZOP study ready to look at all the steps in a batch mode process, but we don't know which kinds of fault or failure are credible and which are not credible, then the HAZOP study becomes a bit unmanageable, because we don't know which cases we should study and which cases need not be studied. And there are too many possible faults usually to study them all. I'm going to show you some examples a little bit later of what kind of cases we might need to consider. So that sort of study, which is based on a pretty simple and short checklist, I think should come before you do the HAZOP study. As an input to it. Then after you complete the main HAZOP study, the HAZOP then becomes an input to what I call the continuous CHAZOP study. Now this is where we look at the entire control system, including all of the networking associated with it and any other PLCs that are part of the control system. And we challenge the design with a quite extensive checklist of questions in order to find the vulnerabilities, as we've discussed before. And the reason why the HAZOP study is important as an input to that is that the HAZOP will tell us what are the reasonable worst case consequences of failures in the control system. So therefore, I think that we need to do a bit of HAZOP before a bit of CHAZOP, sorry, before we do the HAZOP study, and that would be specifically to identify failures in the batch control system. And then after we complete the HAZOP, we can do what you might call the full CHAZOP study. Let me talk for a few minutes about what I call the batch mode CHAZOP study and just try to clarify what I mean by this. So this is appropriate when we have some kind of automatic sequence that the control system will step through. Or a sequence maybe that requires the operator to command the system to proceed to the next step, but then within each step, the various automatic actions take place, such as opening and closing valves and adjusting set points. The CHAZOP for batch mode would be based on a relatively simple brief checklist, which we can provide an example of if required. And what we're trying to do is to identify which types of issue in the control system, such as malfunctions or misoperations, could upset the normal intended operation of the sequence. And these are mostly yes-no questions that we would ask. And you can see 3 examples of challenge questions in the blue box at the bottom of the screen. The first one is, can the operator press the next step button at the wrong time? So supposing the operator has got the option to advance or required to advance to the next step, what happens if the operator doesn't wait for the previous step to be completed? Or is it possible for the operator to delay too long before pressing the next step button? Or maybe some other issue like, can he accidentally press it twice? Or maybe some bounce in the button that causes it to skip forward 2 or more steps at the same time. Now, all we're asking at this stage is it possible for that kind of upset to occur? We don't need to ask about the consequences of it. We just need to ask about the possibility that it could occur. Consequences will be assessed later in the HAZOP study. So we just need to know yes or no. Can it happen? What kind of upsets are credible? The second example is supposing there is a timer or some other permissive that the sequence uses to advance from step to step or to give the operator permission to proceed from step to step. Could there be a malfunction with the timer? Could it be even something like the operator inadvertently missets the timer, maybe to 5 seconds instead of 5 minutes or something like that? Again, all we're trying to ask is it possible? Not worried about consequences at this stage, only possibility. And then the third example question here would be, is it possible that the system could suffer a fault such as a stuck valve? And if that happens, then how does the system behave? And let me show you an example in a moment of where that question was important. So this is a real-world example of an automatic batch mode process for manufacture of a chemical product. The batch sequence included one step that was exothermic. And the control system was programmed so that if any kind of error occurs, such as a stuck valve, the system would command all of the valves to hold last position while the operator gets time to try to resolve what the issue is. And that was considered to be fail-safe. They thought, well, if everything just stays in the same position, that should be safe. Now, what happened one day was a fault occurred in one of the field instruments, and it was detected, but unfortunately it occurred just at the beginning of the exothermic step. So just when the cooling water control valve was starting to open, and it was only slightly open at the time. So the system did what it was programmed to do, which is to hold last position. But unfortunately, last position was only barely cracked open for the cooling water valve. So as a result, there was insufficient cooling. And the result is that the hardware, the process equipment, overheated and suffered some damage. So in that case, clearly, fail-safe was not actually safe. It did not put the process equipment into a safe state. And that kind of situation is exactly why we need to ask the question, how does the system respond if a fault occurs? And then that information will then be fed forward into the HAZOP study. The HAZOP study will then say, well, if the system goes into this state of hold last position, is there any point in the sequence where that would be unsafe? And what would be the consequences of that? So that question, that follow-up question, would be asked in the HAZOP study. And by the way, just before I move on, I would like to mention that that example I just showed was from a book by Trevor Kletz. Now, if you're not familiar with Trevor Kletz, he recently passed away, was one of the great gurus of process safety, been working at ICI for many years, and he really understood and studied and taught process safety concepts in depth. And he's very good at identifying examples and explaining in a very clear, no-nonsense way what process safety really means and what do we really mean by safe. And if you haven't read any of his writings, such as his book called What Went Wrong, then I strongly recommend you get hold of that. And it's an easy read, it's an entertaining read, but it's also a very sobering read for all of us who are involved in process management and process safety. Now let me move on to the real meat of the talk, which is how do we do this main kind of CHAZOP study, which I call continuous CHAZOP. Well, the scope of it is to cover the whole of the control system. It's normally done as a workshop study with several different disciplinary experts present. And typically that workshop lasts for 3 days. I've done quite a few of them myself for different types of systems, large systems, small systems. And generally it always seems to end up requiring about 3 days of workshop. It's based on a detailed checklist that mainly contains what-if questions, but also contains some yes-no questions as well. And that detailed checklist, if you want to get hold of it, then please contact us and we can discuss. We'll certainly be happy to send you a sample on request. And the purpose of the CHAZOP study is to identify any issue in terms of deviation from normal operation or normal behavior in the control system that could ultimately cause a process upset with significant consequences. The boundary of the scope of study in terms of the hardware that we ought to cover, in my opinion, is shown in the blue box on this slide. It would include the panel, the main control panel itself, the PLCs, the ESD system, the UPS, which is the battery backup supply that's dedicated to this system, the operator's workstation or HMI, human machine interface, the IO cards, the network that's associated with the control system, and any other PLCs such as, for example, tank farm management system, or any other dedicated specific control PLCs, and local panels as well, if they have any actual control functions in them. What I would consider to be out of scope would be, on the left side, you can see the power feed. So we certainly consider loss or upset of the power feed to the control system as an issue, but we don't need to understand the root causes of that in detail for CHAZOP. Sometimes those root causes would be studied as a separate type of study, sometimes called electrical HAZOP or eHAZOP. We also don't need to study the wider network in detail, except to be aware whether or not the control system is connected to the wider network. That study is, I think, too specialized to be within the scope of CHAZOP. So I would say put that out to the cybersecurity study. Then on the right side of the blue box, you can see the field equipment, which means the sensors and the final elements, the control elements, such as control valves, shutdown valves, motor control circuits, and so on. That equipment should be covered in the HAZOP study. So we don't need to consider those individual failure cases again in the CHAZOP. But having said that, those failure cases are important as input to the CHAZOP study, and I'll show you a little bit later how we extract that information about failures to put into the CHAZOP study. So input data that we require for the CHAZOP study, the HAZOP report is a really key document. So it's very important to make sure that the HAZOP report is completed and is up to date before we go into CHAZOP. And I think on the next slide, yes, I'm going to show what kind of information we need to extract from the HAZOP report. We also need data sheets for the control system hardware. So we need plenty of detailed information about what is actually there in the system, which cards, which consoles, which modules, etc. Because we will be asking quite a lot of very detailed questions about it, which even the CNI team, control and instrumentation team, may not be familiar with the system to that level of detail, especially if it's a legacy system that's been around for a few years, which is quite commonly the case in CHAZOP study. And then the other thing we need is the architecture of the control system, including the network connections. So what information do we need to extract from the HAZOP report? What we need to do is to go through it to find all of the cases in HAZOP, which are usually listed as causes in the worksheet, which result in, where the root cause could be an upset in the control system, and where the ultimate consequence is some kind of significant upset leading to significant harm. Now, that harm may be a safety issue, for example, a fire and explosion leading to potential injuries. It can be an environmental issue leading to contamination, or it can be a financial issue, for example, some equipment damage, some cost of loss of reputation, or some other financial issues such as downtime or legal implications such as fines, prosecution, compensation, loss of sales, damage to valuable product contained within equipment, and so on, any kind of financial impact. So let me give you an example here. This little diagram shows part of a system that might be used for transferring propylene from a ship into an intermediate storage facility, from where it can then be sent onwards to a polypropylene plant. Now, supposing that the shutdown valve on the inlet of the storage bullets closes inadvertently while we're transferring propylene from the ship. If the transfer pump continues to run, then it could be deadheaded, which might, after a while, lead to some seal damage of the pump, and eventually, in the worst case, that might result in a leak and potentially a fire. So that would be a case where a control system failure, for example, I/O card fault, might inadvertently close that valve and leading to a final consequence. So we need to capture that particular case from the HAZOP, and usually I recommend that we make a little table showing these cases that could arise from control system upsets. And what we need to know for each case is three things really. One is the root cause potentially like a fail high case or a fail low case? So for example, inadvertently closing a shutdown valve would be a fail low case, because usually a shutdown valve, you normally send it a logic 0 signal, or basically no signal, in order to command it to close. So that would be what we would call a fail low case. So we need what type of cause is it? The second thing we need to know is what are the ultimate consequences, assuming no safeguards apply. So in that case, that's a potential propylene leak and fire. And the third thing we need to know is what safeguards were identified for this case. And in this case, quite likely there would be something that would either trip the pump or maybe protect the pump in some other way, for example, a minimum flow loop that might recycle back to the ship. So those safeguards we would write down, and the reason we're interested in those is because we need to confirm that they're going to be sufficiently independent from the root cause when we look at the CHAZOP study. So our preparation from the HAZOP then will be to go through all the HAZOP worksheets and identify all those cases with significant consequences that could arise from control system malfunctions. Now, that might sound like quite a daunting task because you may think, oh, our worksheet, is 500 pages long, HAZOP worksheet. But actually, in practice, you'll find that only a relatively small number of cases actually meet these criteria of potentially being caused by control system upset and having significant consequences if no safeguards are effective. In my experience, it's typically only 3 or 4 cases per node. So it's actually not a difficult job to copy and paste those cases into a separate table, which you can then refer to during the CHAZOP study. Right, so now let's supposing we're getting down to work on the workshop, and we need to decide who needs to be present in the workshop. And the key role is really the workshop chairman. Now, if you've got experience of doing HAZOP study, you'll know that the chairman's role in HAZOP is really very important because he or she is really the key person for keeping the discussions on track and making sure that issues are not kind of glossed over or skipped, and not allowing any party to kind of get away with just giving kind of partial answers or incomplete answers that mean we might not really dig down and discover the underlying issues. And these characteristics of the workshop chairman are even more critical in the CHAZOP study. And from my experience, chairing a CHAZOP is actually more challenging than chairing a HAZOP. One of the reasons is that the team is generally likely to be less familiar with CHAZOP study. Many teams will have never done one before, will not even know really what it is or what's the purpose of it. So the chairman's job to try to keep discussions on track, keep everyone focused on the purpose of the CHAZOP study, avoid the long side discussions, avoid delays while people dig through documents trying to find the answers. And again, trying to avoid the kind of superficial answers or the whitewash that sometimes happens. These are all really key tasks for the chairman in a CHAZOP study. And another important task, actually, which also I believe is more difficult in CHAZOP than in HAZOP, is to make sure that everything is captured in the worksheet. Because the scribe, if you're using a scribe, is again likely to be less familiar with CHAZOP and maybe less aware of what should and should not be written down in the worksheet. So all in all, it's a very challenging task chairing a CHAZOP. Who else do we need to be present in the workshop? Well, we need a multidisciplinary team. The key person is the control systems engineer. And if you can have a representative from the control system vendor, that is absolutely ideal, because really those should be the people who have their fingers right on the knowledge of where the issues lie when we start digging deep into how the control system can malfunction and can misbehave, or how it can be misoperated. So that's really the key discipline that we need. Other disciplines that we need represented: electrical, because we often ask a lot of questions about power feeds, about UPS systems, about how, for example, motor control circuits will behave when they receive incorrect commands, and so forth. Instrument engineers are needed. Network and communication specialists may be needed. Others, you may notice that, for example, process is not there on the list, and HSE is not there on the list. Sometimes we do need some input from these guys, for example, to answer questions about what is the failure mode of such and such a valve, or what redundancy is there, or something like that. But usually those questions hopefully they'll either be obvious from the PNID, so we can read them off directly, or from the data sheets for the hardware, or questions that those people can come into the meeting just to answer a specific question without needing to be there all the time. So you can treat them as being on call for the most part, as long as the documentation is in good shape. Now let's talk about the workflow that we need to go through during the CHAZOP workshop. So this is the way that I handle it. If you think about a HAZOP study, normally the first thing we do is to divide up the scope into sections of process equipment, which we refer to as nodes. Now, the term node has been used for many years, but it's a bit of an unfortunate term because it can be confused with network nodes. And that's not what we're talking about, clearly, with nodes. And so for that reason, I do not use the term nodes to refer to the sections of study within a CHAZOP. I prefer to use a different term, and the term I normally use is functional areas. And the functional areas that I will normally refer to are, most importantly and firstly, the main process control system, DCS or BPCS. The SIS, which is Safety Instrumented System or Emergency Shutdown System, will be another functional area to look at. Panels, local panels, any panel that has got control functions within it. If it's just indicators, then we probably don't really need to look at it in detail. Workstations for where the operator interacts with the control systems, that needs to be another functional area for study. Any separate PLCs, such as, for example, tank management systems, and any network equipment that's not already covered in the other functional areas. So that's usually how I will divide it up into logical sections for study. Now, within each functional area, we then apply what in HAZOP would be called deviations. Now, rather than trying to apply the HAZOP deviations, such as more flow, no flow, high pressure, low pressure, and all those, we have a different set of prompt terms or categories of failure or categories of issue to look at, which I refer to as failure classes. And some examples of failure classes are shown on the left side of this slide, such as power supply to a specific functional area, the hardware within a functional area, communications within and to and from a functional area, any security issue relating to that functional area, any human factors relating to it, maintainability, overrides, and a whole lot of others. So we have usually about 12 different failure classes altogether. So in HAZOP terms, those failure classes are like deviations. And then we need to look at what in HAZOP we would call causes. So this is where we're looking for specific issues within each failure class. So let's take the example of a power supply failure class. Within that, what kind of power supply issues could we have? Well, maybe we have a problem with the AC feed to a functional area, such as a feeder going down from a circuit breaker failing. Maybe we don't lose the whole feed, but maybe we lose only one phase of the feed. Maybe we have a AC to DC converter or power supply, which may fail in a number of different ways. It could fail low, it could fail high, it could fail intermittent, it could send dirty power, various different failure modes. And we would need to ask the control system or the engineer to explain the possible failure modes to us. We could suffer over voltage, under voltage, dirty power, and potentially various other issues relating to the power supply. So all of these would be what we, in HAZOP terms, we would call causes. So that's just one example of the causes that, set of causes that we need to go through one by one. And to go through each of those, we can follow through a checklist, which, as I mentioned earlier, it has some what if questions. So that will be, for example, what if the AC power feed to this functional area is lost? And then there will also be some yes/no questions. So let me show you just a few examples. First one, what if the AC power feed is lost? Second one, what if the I/O card fails high or fails low or fails with frozen output or maybe some other kind of output such as fluctuating? or noisy output? What would happen if there's a network switch failure? So those are all what if questions. And then here's a couple of examples of yes/no questions. The first one relating to security. Is there a way to prevent unauthorized access to the control system cabinets? Second one, has a cybersecurity assessment been performed? So that is quite a wide-ranging question, but really that's just a prompt to confirm that a separate assessment has been done for this scope, the functional area that we're discussing. We would not want to embark on trying to perform such an assessment in detail during the CHAZOP because it's too specialized and requires a different type of methodology. So really all I recommend in CHAZOP is just to ask the question yes or no, has it been done? And if no, then why not? And is it necessary? And when will it be done? So that may end up raising a recommendation for further attention. So the way in which those questions are addressed is the what if questions would be handled in the same way as a HAZOP cause. So you'll work through causes and then consequences and then safeguards and recommendations. The yes/no questions are really just there to be prompts. So usually for those, you will simply write in the worksheet, you will discuss, and then you will write the answer is yes, because, and provide some supporting evidence, or no, because, and provide some supporting evidence. And then if necessary, usually if the answer is no, then it may be a prompt to write a recommendation for further action. So for the for the what if questions, we follow the HAZOP methodology. And the first thing we would need to do usually is if we're trying to do some kind of risk ranking for each case, similar to what is often done in HAZOP, then we need to try to identify the frequency of when the root cause failure or upset may occur. Now that can be quite difficult for CHAZOP actually, because there may be relatively little data available for that. And that can be something of a stumbling block. Sometimes if the frequency is not known, we can make an assumption about the frequency, which is typically, we maybe assume 0.1 times a year for a typical failure or upset or misoperation event, and then work through with that frequency to see if it yields a relatively high risk ranking at the end of it. And if it does, then that might prompt us to say, looks like we need to investigate this in more detail and try to assess whether that frequency is a reasonable guess, whether it's on the high side or even on the low side, to tell us whether this case merits further investigation. So that might be a recommendation arising from a case where you see there might be a concern, in this case, about the potential risk arising from that cause, if the frequency is not already well known. The second thing that we do then, similar to HAZOP, having assessed the cause and the frequency, is then we assess the reasonable worst case consequences. Now, the consequences we're interested in is the harm that may actually arise to the process equipment. So not just focusing on the control system, but beyond that, to out there in the field. Can we actually have a leak, a fire, an explosion, an environmental incident, some equipment damage, some other costly event like some downtime? And that is where the information that we extracted from the HAZOP comes in useful. Because what we can do is quickly scan through that list of cases that we extracted from the HAZOP report to find which cases are relevant to the specific cause that we're looking at now. And thereby we can say, well, looks like if this happens, the potential worst case consequence is XYZ, whatever it is, and then copy that into our CHAZOP worksheet. We're not saying it will always happen, we're just saying that is the potential worst case consequence. Then we will evaluate the safeguards, and I'm going to talk about the potential safeguards in a moment. Next, we need to assess whether those safeguards are sufficient, and that may be based on another risk ranking, so where we calculate the likelihood after safeguards are applied, and then also address the potential worst case severity of that case. So then typically that will be looked up in a risk matrix to find out whether the risk is tolerable or intolerable. And if we have concerns about the risk, or if we feel that the information is not enough, or if we found some issue during the discussions relating to this point, then we may write a recommendation for redesign or for further investigation. Now, what about safeguards? What kind of safeguards should we apply in the CHAZOP study? So we can start off by applying the same safeguards that were applied in the HAZOP study for the reasonable worst case. But we need to make sure that those safeguards will still be available when the failure cause that we're studying has actually occurred. So if the failure cause, for example, was a CPU failure in the control system, then we may need to assume that every safeguard that requires correct operation of the control system becomes unavailable. So that could knock out alarms, control loops, DCS-based trips, and any other kind of active safeguard that relies on the operation of the control system. But there may be other kinds of safeguards which are provided by other systems. For example, the control system itself may have alarms, such as a watchdog alarm or a communication failure alarm, or whatever it may be. And if the operator receives those alarms, and if he has information about what to do when those alarms come, and he can take an appropriate action with a reasonable amount of time to respond before the consequence occurs, then we can take credit for those system alarms in the CHAZOP. And that's a bit different from the HAZOP study, because typically we wouldn't consider those types of alarms as safeguards in HAZOP. What else? Well, there may be redundancy in the control system, and that could be a potential safeguard. But again, bear in mind that if the system does not automatically switch over to a redundant channel, but relies on an operator action to switch over, then the operator needs to be prompted in some way to take that switchover action. So you would need to make sure that he would be aware and that he knows what to do and how to switch over, and that he's also authorized to do that as well. Other passive systems built into the controls equipment, such as check valves and relief valves, should still be available, even in the event of a control system failure. There may be backup systems, such as a UPS, uninterruptible power supply, maybe an emergency diesel generator that could kick in or that could be started by the operator. And then there should also be, for the most extreme cases, there would be the ESD system, or safety instrumented system. And as long as it is sufficiently independent from the control system, then that should remain valid as a safeguard for our CHAZOP cases. Now, what about considering software failure cases? Well, software clearly is part of the control system and clearly needs to be evaluated at some time. But we can't really assess it in the same way that we do other kinds of failures, like misoperations or hardware failures, in a deterministic way, because there are too many different ways in which software can fail. And the other issue with trying to assess software failure is, how are we going to calculate or estimate the likelihood or probability or frequency of failure? With hardware failures, we can assess that because it's reasonable to assume constant failure rates using lambda values that we can look up in databases, but not so with software. We haven't reached a level of kind of software technology that allows us to calculate a probability of failure in that way. So typically then in CHAZOP, the best we can do is to look at some yes-no questions, really to try to confirm that the software is sufficiently robust. And that would be to ask questions like, are the software updates controlled? Is the application software validated? And has a software criticality analysis been performed really to identify how bad could it be if a software failure occurs? What could the worst case consequence actually be? So that's really about as far as we can go, I would say, in a CHAZOP study with regard to software failures. If we're talking about malfunction of the software, or should we say software bugs in the software itself. Okay, we're almost at the end of what I wanted to cover. Let me give you some specific examples. So let's say we're studying functional area DCS, and we're looking at failure class software. So we're looking at software issues. And when we work down our checklist, we find there is a question in the checklist that says, what if the application software fails? In other words, there's a bug in it, and that bug results in a false zero output on the I/O cards. So maybe the software crashes, or maybe it gives a ridiculous result, which like a negative number or something, which the I/O cards then interpret as zero and sends the zero, for example, zero position to a control valve, or commands a shutdown valve to close, something like that. So that would be the cause. And then we would identify the consequence by looking at all of those fail low cases that we identified in the HAZOP study. And that will tell us what is the reasonable worst case consequence. And from that should actually tell us whether a software criticality analysis is appropriate. Because if that's a very serious consequence, at least not well controlled by safeguards, then we might say, well, this software is really mission critical, and we need to be looking at it in very fine detail to confirm that the validation of this software was highly robust. However, we do still have some safeguards that may still be available, as long as we're not relying on safeguards that could be knocked out in such a case where there's been an application software failure, for example, a freeze. So there may be still some independent safeguards remaining in the control system that could be considered to be independent of this particular software failure. There will also be other safeguards within the control system itself, such as watchdog alarm or redundant channels. And then there may also be passive safeguards, relief valves, check valves, and the ESD system should be still available. So those would be documented as safeguards and taken into account in the risk ranking. So that is just one example of how we might evaluate one case out of many, probably hundreds of cases that we will cover in a typical CHAZOP workshop. Right, let me give you a specific example of a CHAZOP study that I executed recently. I chaired this study in a gas metering plant for a client in the Middle East. The reason that the client decided to perform a CHAZOP study was that they had had a maintenance-related incident on their control system. According to the manual for the control system, it was possible for them to swap out one particular card within the PLC rack without shutting down the control system. In other words, it was supposed to be hot swappable. So they tried it, but unfortunately, as soon as they removed the old card, the whole of the control system tripped and it shut down the whole process. And as a result, the supply of sales gas to a number of large consumers was cut, and there was a lot of downtime, a lot of outage on some downstream plants, which actually ended up was a very costly event. So they decided to look at the system in more detail to find out whether there were any other lurking issues not yet discovered that they would like to deal with in order to improve the availability or the uptime of their gas supply to their clients. So we performed the CHAZOP study, but the first problem we hit was that there was not much of a HAZOP study done previously on the gas metering equipment. And without the HAZOP, we couldn't really evaluate the worst case consequences. So the first thing we did was to do a mini HAZOP for the specific cases that could result from control system upsets. So that was really only studying maybe 8 or 10 specific cases following a typical HAZOP methodology. And one of the issues we found was that the previous analysis they had done of risks was significantly out of date because the original operating concept for the plant was that it would be mostly unmanned. But since startup, they'd found that the plant needed to be manned most of the time. So as a result, the safety consequences of potential hazards were higher than originally evaluated. So we actually had to back up and do quite a bit of reanalysis of their previous process hazard analysis. However, having done that, that then equipped us with the information we needed to go into do the full CHAZOP study. And we found quite a number of interesting issues. And one of the most significant ones that for me made the whole CHAZOP study worthwhile was we found that some of the equipment was powered from a single circuit breaker that was in a remote location, not within the boundary of this client's equipment, not even under this client's control, but owned and operated by a different company. And we found that if this single circuit breaker tripped, it would lead to the same consequence again, that the entire unit would shut down, leading to a loss of gas supply to all of the consumers. And to me, that was really the can we say the value of this whole CHAZOP study. It paid for, to me, it paid for the CHAZOP study many times over, just finding that one result, because clearly that was the major potential source of loss of availability for their plant. So that was the main recommendation coming out of this study, was to address that and to try to deal with the lack of redundancy in that particular power supply. There were quite a number of other issues that we found as well. And some of them were actually that the system was actually not as well understood. They were lacking some information on how the system would behave in certain upset scenarios. So all in all, very interesting, and I think a very worthwhile CHAZOP study there for really relatively little cost. So that's brought us to the end of what I want to talk about today. Thank you very much for watching all the way to the end. If you have questions, I'll be more than happy to take them. Please contact us afterwards by email, as you can see my email address on the screen now. If we have made you hungry to learn more about CHAZOP, we have some training materials available. We can either offer these as a workshop study, either face-to-face or remotely, or we can offer you packages of training materials for self-study, which you study by yourself, and then we will have a kind of an online discussion afterwards to address any questions that you have. So if you'd like to see a sample of those training materials, please let us know and we'll be more than happy to provide those. So that's the end of my talk for today. Thank you for your attention, and if you have questions, I'll be happy to take them now.